It's been 1 week since you looked at me. Cock your head to the side and said I'm angry.
In this video, we're going to talk about sequences for section 9.4. Now, infinite sequences, one of the most natural ways to study patterns in mathematics is to look at an ordered progression of numbers called a sequence. Here are some examples of sequences. 5, 10, 15, 20, 25. 2, 4, 8, 16, 32. And then 2 to the k power. 1 over k, where k is 1, 2, 3, all the way up through infinity. And then a sub 1, a sub 2, a sub 3, all the way to a sub k. Now the first of these four is a finite sequence, while the other three are infinite sequences. Notice that in 2 and 3 we're able to define a rule that gives the kth number of the sequence called the kth term as a function of k. In 4 we don't have a rule, but notice how we can use subscript notation a sub k to identify the kth term of a general infinite sequence. In this sense, an infinite sequence can be thought of as a function that assigns a unique number a sub k to each natural number k. Now you should have been able to pick out how the sequence is transformed. Like in the first one, every sequence goes up by 5. In the second one, we're taking powers of 2. 2 to the first power is 2, 2 to the second power is 4, so on and so forth. Now we're going to move on to example 1. Defining a sequence explicitly. Find the first 6 terms in the 100th term of the explicitly defined sequence. So a sub 1 for our first term will be 1 squared minus 1, which is 0. A sub 2 will be 2 squared minus 1, which is 3. A sub 3 will be 3 squared minus 1, which is 8. A sub 4 will be 4 squared minus 1, which is 15. A sub 5 will be 5 squared minus 1, which is 24. A sub 6 will be 6 squared minus 1, which is 36. And then a sub 100 will be 100 squared minus 1, which would be 9,999. Moving on to B. U sub 1, 1 plus 1 over 1, which is 2. U sub 2 will be 2 plus 1 over 2, which is 3 over 2. U sub 3 will be 3 plus 1 over 3, which is 4 over 3. U sub 4 will be 4 plus 1, which is 5 over 4. U sub 5 will be 5 plus 1, which is 6 over 5. U sub 6 will be 6 plus 1, which is 7 over 6. Then U sub 100 will be 100 plus 1, which is 101 over 100. Explicit formulas are the easiest to work with, but there are other ways to define sequences. For example, we can specify values for the first term or terms of a sequence, then define each of the following terms recursively by a formula relating it to previous terms. Example 2 shows how this is done. So, in example 2, find the first 4 terms and the 8th term of the recursively defined sequence. So, B1 is 3. That means B2 will be B1 plus 2, or 3 plus 2, which is 5. B3 will be B sub 2 plus 2, which would be 5 plus 2, which is 7. B4 will be B3 plus 2, or 9. Now, if we have to find the 8th term, b sub 8, that will really be our b sub 7 term plus 2. But what we really need to do, if you notice, the sequence goes 3, 5, 7, 9, like this. So it's going up by 2 each time. So really, instead of b sub 7 plus 2, we're going to take our first term, then we're going to take our 7th term times 2. Because really what we're doing, we're taking our first term b, and we're adding 2 to it 7 times to get to the 8th term. So our 8th term will be 17. B sub 8 will be 17. Now if you look at b, our first term is 8. Our second term will be a sub 1 minus 4, or 8 minus 4, which is 4. Our third term, be a sub 2 minus 4, so it'll be 4 minus 4, or 0. Our fourth term will be a sub 3 minus 4, or 0 minus 4, or negative 4. So what we're doing each time, we're subtracting 4. So to find the 8th term, that will be my original term plus a 7 times a negative 4. It's a negative 4 because this is a minus 4 here. That'll be negative 20. Now if you list out the terms, you'll see 8, 4, 0, negative 4, negative 8, negative 12, negative 16, negative 20. So there's our sequence so far. Here's our first term, second, third, fourth, fifth, sixth, seventh, eighth. It's exactly what we got above. Now, finding it recursively is a heck of a lot easier than listing all the numbers, especially if you have to find the 100th term. So my 100th term will be 8 plus 99 times negative 4. So when you do that in your calculator, 8 plus 99 times a negative 4, we get a negative 388. I don't know about you, but I really don't want to write out this sequence 100 times. It'd be a lot of waste of my time. Just as we are concerned with the end behavior of functions, we'll also be concerned with the end behavior of sequences. Now let a sub n be a sequence of real numbers and consider the limit of a sub n as n approaches infinity. If the limit is a finite number, the sequence converges and L is the limit of the sequence. If the limit is infinite or non-existent, the sequence diverges. You'll see what we mean here in example 3. Now determine whether the sequence converges or diverges. If it converges, give the limit. So this is what we're going to find the limit of. The limit of 1 over n as n approaches infinity. Now from our previous chapters, you know if you take 1 divided by a super huge number like infinity, it's going to go to 0. It's going to get smaller and smaller and eventually go to 0. So this will converge to 0. Now if you look at b, we're not given a recursive formula here, so we have to come up with one, which will be n plus 1 over n, which I can really simplify to 1 plus 1 over n. So this is what I'm going to find the limit of. So what we're going to have here, the limit of 1 plus 1 over n as n approaches infinity, 1 plus 0 or 1. So this converges to 1. Now in C, again, we don't have what we need, but it'll be 2n. If our first term is 1, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. It's going to keep going on and on like that. So it'll be 2 to the n. So we're going to find the limit of 2n as n approaches infinity, which will be infinity. 2 times infinity is 2 infinity. So this actually diverges according to our definition of convergence and divergence. Now if you look at D, here's our recursive formula. So we're going to find the limit of -1 to the n power as n approaches infinity. Now this is going to be a little bit different here. If we let n equal 1, -1 to the first power is -1. -1 to the second power would be +1. -1 to the third power would be -1. -1 to the fourth power would be +1, so on and so forth. So really, this will not exist. So this diverges. So the limit oscillates between -1 and +1. Now if you look at E, again, we don't have a recursive formula, so this would actually be, if you notice, 1, 4, 9, 16. 1, 4, 9, and 16 are the perfect squares. So we're to find the limit of 1 over n squared as n approaches infinity. This will equal 0. So this converges to 0. It might help to review the rules for finding the end behavior asymptotes of rational functions, because those same rules apply to sequences that are rational functions of n, as in example 4. So really, we're going to be finding the limit of 3n over n plus 1 as n approaches infinity. Well, our leading term, this will really be 3n over n, which will be 3. So there's my limit. So this converges to 3. So the limit of 3n over n plus 1 as n approaches infinity. If we take a look at our leading terms, that's what we get for 3. Now if you look at B, the limit of 5n squared over n cubed plus 1 as n approaches infinity. That will really be 5n squared over n cubed, which will simplify to 5 over n, which will be 0. As n approaches infinity, it will be 0, so this converges to 0. If we look at C, what we're going to have, it'll be n cubed over n squared, which will simply be n. The limit as n approaches infinity will be infinity, so this diverges. Now if we look at D, what we'll have, this will really be 3n over -3n, which simplifies to -1. So this converges to -1. And there you have it, nice easy limits, stuff we learned early in the first semester.